Okay, I think we should start. Today we're happy to have Arindam Chatterjee from the Indian Statistical Institute. Arindam worked with Emmanuel Dries on his PhD, working on dark matter within supersymmetry when back when it was cool. Now he only works on dark matter. And today he's going to tell us about various dark matter models and how to look for them.
Thank you. Thank you for giving me the opportunity to present some of the works. The title is Struggles in the Dark Protein Dark Matter Models. Try to be a bit philosophical with this before testing. This is the plan of the talk that first I will give introduction, motivation to dark matter, and this is just primordial black holes as the simplest model. Requires no extension. Standard model, just PBAs would be incidents. I would discuss a little bit about them before motivating other particle dark matter models. Then I'll move on to dark matter within a well-motivated model. By well-motivated, I simply mean that the model is not designed to address the dark matter issue, but anyway has it. And my favorite is supersymmetry there, so with a couple of SUSY dark matter candidates. And then I'll move on to self-interacting dark matter. There are some tensions, as you might already know, in the small-scale structure formation within Laplacidium with collision-based dark matter. So self-interactions in dark matter might help, but many SUSY dark matter models, for example, is not designed to have large self-interactions. That requires actually spatial model building. So we tried doing that. And in these cases, I would try to comment on the prospect of thermal dark matter, because the most well-motivated production mechanism is still probably the wind, the thermal production of wind, because it's not sensitive to the initial conditions. But I would discuss the prospect of thermal dark matter in the last two scenarios before moving to a non-thermal production mechanism, a particular one there are many. So, okay, thank you. This is the motivation for having dark matter in the first place. Of course, usual motivations, galaxy rotation curves and bullet cluster. The point is that we have evidence of non-luminous matter on all cosmological scales as well as astrophysical scales, so that is interesting. It's not like one particular thing, but it's like on all scales. So, as you know, that the most precision abundance comes from Planck, and that is presently at 0.12 omega h squared. So, coming to primordial black holes as dark matter candidate, as I said, that these are the simplest ones. The mass range of 10 power 15 grams and above, they are stable against Hawking radiation. So the smaller PBAs are ruled out as dark matter candidates because they would not survive until today. And there are also bounds from indirect detections for around 10 power 15 gram PBAs. Bigger than that, it's fine as far as evaporation is concerned. But then there are a host of femtolensing and microlensing constraints on them, and the most recent one, as you might have heard of, this is a slightly old paper, 1701, but got published in Nature, I think April this year itself. From Subaru HSC, it looks at microlensing of Milky Way as well as M31, that is Andromeda, and looks at Andromeda stars, but dark matter in both Milky Way and Andromeda could contribute to the microlensing, and it tries to estimate events with PBH, primordial black hole dark matter, since PBH is supposed to be dense when it passes through the lens, the camera. They're observing many stars at the same point. So when it's a PBH passes in between, it would cause microlensing, and they get only one candidate event, I think, and that's pretty bad. So they rule out a significant part of what has not been probed earlier, that is 10 power 21 to 10 power 28 grams or something. PBH cannot be the largest contributor to the DM relief density after this observation. Only a very small narrow mass window I think is still left out. But the second difficulty about PBH that I would like to describe is the production of PBH. Since it is primordial, it usually requires a large primordial perturbation that has to be generated during inflation. Now, to give you to keep things in perspective, let us see. This is some of our work, not geared to produce PBH, but the plot that you see here is the plot that you see here is the scalar power spectrum after inflation. This is already a polynomial potential fit to observe, get large tensor to scalar as well as some gravitational wave signature at small scales. But just to give you a perspective, the scalar power starts at about 10 power minus 8.5 or so, and production of PBH requires the scalar power to pick up to 10 power minus 2 in order to get anything substantial. And if you consider this mass formula, so it's like the scales, the perturbation exits during inflation, the scales exit, they re-enter, and the perturbation at that particular scale, which corresponds to this 10 power 20 or 24 grams of mass of PBH, you can see from here that the K you need is about 10 power 13 or so. So that would be somewhere here. So it's like the power spectrum goes like this, and suddenly you need a peak here to produce your 10 power 20 grams of massive PBH, where it should go to 10 power minus 2 and again fall back. That is, so this is what you need. This is the inside story, and it's not constrained so far because Planck only constraints up to somewhere here, and then there are like spectral, CMB spectral distortion constraints are there, but they are for now quite weak. They stand here, but still 10 power minus 2 is a bit high. So you need to tweak with the inflation models a lot. And you will realize that, so this is the group, Manuel and NC, Irfani, they did some work. And running mass inflation and some other models, there are a few inflation models which are not quite simple. They would give something similar. And of course then, Yanagida and collaborators, they continuously have worked on two-stage inflation models. So you have to end the first stage of inflation before this scale, somewhere here, and start the second stage, and in between you could get a peak in the scalar power somehow. So this has to be tuned here. So I personally don't think this is a very good idea, given that the Planck, so far the cosmological observations fit very well to the standard slow roll single field inflation models. So I move on to now particle dark matter candidates. My favorite first within well-motivated model, meaning as I said that the model is not designed to have dark matter, but has a dark matter candidate anywhere that is supersymmetric. With some usual motivation for SUSY. I also speak that the dark matter motivation is not really known. The point is that if there is R parity, it forbids proton decay via renormalizable operators, although one could have non-renormalizable dimension I consistent with R parity, but it naturally gives the lightest SUSY particle stable. It naturally keeps that stable, and if that is neutral, then this will be the dark matter candidate. So neutralinos are well studied. Now, why do we care so much about? Of course, it's nice to have a dark matter in the model. That is true, but it also plays a crucial role in supersymmetry discovery or constraining supersymmetry, because LSP or any such model, like you could take extra dimensions with capability, something like that, because when it appears as LSP, it dictates the cascades, the decay cascades of heavier particles that we produce. For example, for SUSY, it would be the heavier spheres, which has a larger production cross-section, or electroweakinos, and then depending on the nature of the LSP, the decay products would show up as the signature. So most SUSY plots, SUSY constraints, I assume a simple neutralino LSP, but it is probably worth looking at some other LSPs to see what signatures of stop or Higgs-Inos could be. At least it will help in constraining a more general SUSY framework, rather than picking up simplified scenarios, and experiments are already doing it. So I will not talk much about the neutralino. I will move to S neutrino the other candidate in supersymmetry. So I will move to S neutrino, and as we all know, left neutrino. First, let me start with a simple MSSM light spectrum with left neutrino as per LSP. I would explain what I mean by MSSM light, but so this was ruled out long back from direct detection, as you know that this has a strong Z coupling, and the direct detection cross section would be like 6 or 7 orders of magnitude higher compared to what the current norms have. So it's like gone. But of course, S neutrino, left neutrino LSP, MSSM LSP would be compatible with other gravitino-axion kind of dark matter candidates or actual LSP, because S neutrino would go to a neutrino and a gravitino, so it's like missing ET going to missing ET for collider does not matter. There is another interesting possibility that has been explored by all these groups here. That was if there is a small mass split between the CP even and the CP odd part, because S neutrino, as you know, is a complex scalar, so I could split the CP even and the CP odd part. There are two real scalar fields in it. So if there is a small mass splitting, that prevents the direct detection cross section, which is mediated by Z, because Z couples to the CP even part and the CP odd part, not like CP even Z, that's orbital. So I will explain that in a moment. But if there is a small mass split between the CP even and CP odd part of the S neutrino, then direct detection can be forbidden at tree level. That's the message I want to convey. So in that case, it can be an MSSM LSP. So let's see. This is a model. I don't like so much models, but the model is like SUSY type 2C, so because as we know that MSSM does not address the neutrino mass, so neutrino mass is automatically in it because this is designed for addressing neutrino mass. But the thing that I want to emphasize phenomenologically is that the low energy spectrum of this model looks exactly like MSSM. All the other triplets that you see, they are very heavy. So they are essentially decoupled from the spectrum, and you would not know if they are there or not. So when I'm looking for SUSY at LHC, for example, the signature could just be like an MSSM with a S neutrino as the LSP, even with all this jargon that is present. In addition, you get a help that is a neutrino mass works out fine. This time I'll show how. So here I just wrote down the superpotential and the soft breaking terms. The point is that the heavy fields, they take an induced bit, that is a usual type 2 seesaw scenario where you have a scalar triplet, and that is a supersymmetric version of that. So the point is, the treat is here. Here, as you see, that this is the neutrino, complex scalar field, and there is this delta m square present that will create a split between the CP even and the CP odd part. I explicitly write down the mass eigenstates below, and here we demand that this mass split delta m square has to be of the order of few hundreds of keV. I will tell why in order to evade the direct search completely. This has a consequence. A large split in the CP even and the CP odd partners also create a large radiative contribution to the neutrino mass itself. And here you could see the expression. Now this has to be however tuned, because we know neutrinos are like of 0.1 electron volt or so. Now 100 keV or 500 keV CP even CP odd mass split would usually give a keV or something, a keV order neutrino, because you get some suppression from the loop, but rest is just there. These are the expressions. Its computations have been checked by various groups, and this works out. So what one needs here is a relation between the gaugino mass parameters in order to have additional cancellations of 1 part in 10 power 4 or 5 in order to get the right neutrino mass. That's the cost that we have to pay here. So that is here is R1 and R2. R1 is basically M1, that is the Bino mass parameter. They appear because they go in the loop, that's the reason. neutrinos, neutrino, and the gaugino loop. That's the loop that's giving the mass. So this is R1 and R2. R1 is proportional to 0 mass, R2 proportional to 0 mass, and for a cancellation, you need the relative sign between M1 and M2, as well as a ratio of something like 1:30. So now this might sound like a complicated thing, and it's probably a bit, I mean, phenomenologically, we typically do not associate M1 and M2 with differing by a factor of 30 for no reason. But if you think of some of the non-universal gaugino mass models that have been studied like long back here, I see Dries in 85, and then it's paper by Elisa, 85 as well. And there is a more recent paper by this group, Chakraborty, Mohanty, and who has sort of explicitly worked out several such non-universal models. The list is not infinite. It's like finitely many, but it's there are certain breaking schemes which could give you this ratio. So you have, for example, in M-Sugra, we assume a common mass for all gauginos at a high scale. In this case, you have an extra Planck suppressed term, that is the trace of F phi F over MP, the term that I write there. And of course, this phi would be a specific representation of whatever heavier gauge group that you have of that, a symmetric representation of that. And for this particular breaking chain that I give from their paper, it works out, this ratio works out to 230 to -1 or so. So that's the kind of thing that we need, and if you like a theoretical person, you could get it from a high scale model. So then coming to the dark matter aspects, that is the main issue here is evading the direct search. So this is the Z coupling that I try to write, and as I said that the Z boson couples with the CP even and the CP odd part, and if you could create a mass splitting of like 500 keV or so, that would be enough, because we know that the galactic escape velocity is above this, and written probably slightly larger number, but it does not matter so much. So basically the half mv squared of the incoming particle has to be slightly smaller than the mass splitting, and then you don't excite the heavier state in direct detection. That's the simple idea, and for a few hundred keV it works out fine. Okay. So of course there could be some events, because we assume dark matter velocity distribution to be Boltzmann, Maxwell-Boltzmann with a cutoff or something like that, and some events from the tail could be there, but you could simply take like delta m to be greater than half mv escape square, and then that works fine for to event the direct search. There will be loop processes that we have not yet evaluated, and we are in the process of evaluating it. It's taking some time. We will have to check that, because DD bounds are getting stronger every day, and we could forbid the tree level thing, but there could be loop surface processes that we should mention. This is the status of this is the bound from xenon 1 Ti, and here you could see that these S neutrinos, although I forbid the Z coupling, it's still, there is a D term contribution. It couples to the Higgses, and Higgs mediation processes would be there. That's the reason, with coupling strengths of the order of gauge coupling. So there will be still some direct detection. But since Higgs couplings to the nucleons are much weaker compared to Z coupling, so the bound is much weaker this time. It still survives up to about 550 GeV or so, and then after 550 GeV or so. Less than that, this part is ruled out by DD. Okay. So now coming to the relic density part, we first people thought of.
Sorry, go back. I didn't understand the last part. What did you say? The Higgs coupling and the Z coupling. So now that's your section.
So the thing is that S neutrino is SU2. It comes from SU2 doublet. That's the problem it had, right? It couples to Z. That was the problem. But that Z coupling has CP even and CP odd scalars. Z couples between them. So if I make one of them heavy, a small mass split of like order 500 keV or so, which has no significance for LHC, but it stops the direct detection.
No, but my point is that in direct detection, you have your coherence at that term, so your links and Z0 coupling. If you just show the cross-section, it's misleading because we see rates, not cross-section.
Right.
So where does the one signal is a coherent interaction, one is not. One is just spin independent, one is just spin dependent.
Yes, from Z you could also get spin dependent. This is the spin independent part that I showed. Spin dependent in this case will be much weaker.
This is a cross-section per nuclei or cross-section total?
Sorry?
Is it
This
per
is just
report?
this is per nucleus. I think it's on proton. So what I wanted to say is that the Higgs mediation process would also be there from the D-term contributions, and that is what is still contributing. So we still get some cross section. It's not zero even after we forbid the Z. The H is still there, and that's why we get this. But Higgs coupling to the quarks are much weaker. Correspondingly, when we translate them to Higgs coupling to the nucleon, there are strange quark uncertainties and this and that. So, but the thing is, they are much weaker. So that's the problem. Here is the relic abundance. Since now we have like dark matter, anti-dark matter could be connected to lepton asymmetry and baryon asymmetry because this is a type 2 seesaw. So the heavy scalars now can decay to create the lepton asymmetry. It will be connected to the dark matter asymmetry. The point we are trying to make is that, however, there will be dm bar oscillation in this case. And asymmetric production mechanism would work only if the dark matter mass is heavier than, because the oscillation starts after electroweak symmetry breaking. So the dark matter should have to decouple electroweak symmetry breaking in order to preserve the asymmetric production, asymmetric contribution. But that requires, since electroweak symmetry breaking scale is about 100 GeV or so we multiply by 20, so about 2 GeV, so dark matter has to be heavier than 2.5 GeV or so. That's that we thought is not a, we wanted a neutrino light. So this is the oscillation contribution that will wash out the symmetry after electroweak symmetry breaking. So we, since the initial asymmetry would be washed out anyway, we studied a simple thermal production mechanism. And that is this, it's the usual thermal production. In the left side plot, I just show how the relic density goes when we have co-annihilation with a Bino, and I think with some other strongly interacting particle or particle that is strong, that has stronger interactions compared to the S neutrino itself or similar interactions. So point is that with no co-annihilations, remember it comes with a doublet lepton partner anyway, because this is a part of a C2 doublet. So that co-annihilation would be there, but with just that, you get the right relic density at about 500 GeV, 5 to 600 GeV would give you the right thermal relic density. To go to the lower mass, it is underabundant. So there, if we co-annihilate it with the Bino, co-annihilation raises the relic abundance in this case, because Bino itself interacts weaker than the S neutrino. The unit itself interacts weaker compared to the S neutrino. If we want to get the right relic at a higher mass, we have to co-annihilate with either Higgs-Sinos or stops, bottoms, depending on the mass splitting, and so on. We could adjust the scenario. Just by itself, just by left to itself, the S neutrino has SU2 gauge coupling, so the mass for right thermal relic abundance would be around 500 GeV. And here I show, on the left, I show a Bino co-annihilation. The blue line is a Bino co-annihilation plot, and you see that it generally gives a higher relic abundance when co-annihilated with the Bino. These are the benchmarks. It shows roughly the same thing that I have spoken about for this. So you see that always we get the right co-annihilation to get the right relic abundance between 300 to whatever, but as I said, the direct detection already rules it out up to 550 or so. So it does not matter at the lower mass, it's not there anymore. Here is the collider implications for having a S neutrino. As I said, that it's important to study various LSP candidates because the SUSY spectrum, LSP is appearing at the bottom of the SUSY spectrum and affects all the cascades. So the signature very much depends on the nature of LSP. Here we take a simple spectrum with the Neutrino stop, and there is this Neutrino, but now S neutrino. S neutrino sits at the bottom of the spectrum, because now, as I said, that this thing would be allowed. Of course, if there is a gravitino or axino kind of dark matter candidate, this would be allowed anyway, so the signature would be the same. But this is the thing that we studied, the signature of a stop or Neutrino. And this is the interesting part. When you have a Majorana fermion sitting over a charged lepton, you could produce two same sign leptons, which is nice. And if we start from a stop, because stop goes to top and the neutralino, so that top could give me one more lepton, and we could make a 3 lepton signature. But because of the Majorana nature of this neutralino, since it could go to both sign leptons, it actually has 25% branching to lepton star, lepton, lepton star, as well as some 50% to this neutrinos. That's how it branches usually. So what you would get from here is 2 same sign leptons for each of the neutralino that I pick, and I could take lepton from the W that I get from the top, coming from stop. So I make it same sign and I get 3 same sign leptons, which is amazing because this signature has almost no standard model background. So we were happy. And till then there was no, of course this comes with SS2L and so on, but SS3L is pretty hard to get even within a simple supersymmetric framework, and this is a low energy MSSM light framework that could give you same sign tri-lepton. So this is, of course, if there is a Chatterjee in between the stop and the S neutrino, the signal, the branching ratios would dilute because we are very much using the fact that the stop goes to top and a neutralino gives us both signs of leptons. So if there is a Chatterjee that comes in between them, that's nice. So, I mean, signal significance would drop by. This is an old analysis we have not updated yet, keeping in mind the current constraints, but and updated the benchmarks. So since there is almost no background, we thought that 5 events with some very small background, so we just tuned the benchmarks to have about 5 events, and this roughly gives you the reach at LHC. This is for 100 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ So this is what we have to say about the Leibniz neutrino. Now coming to as I said that I would not be talking about neutralinos because you hear about neutralinos so much. And this is now the story of the Leibniz neutrinos, much simpler compared to the previous one because we don't even need the high scale extensions. Leibniz neutrino, the simplest way to give a neutrino mass is just to introduce a small coupling with the right neutrino. I mean, neutrino for standard model and neutrino for the SOSI version of it. And since it is a singlet, of course, you can have a small Majorana-like mass term for it in the superpotential as well as in the soft term. Now, this was first in the dark matter context. This group Asaka, Ishigawata, and Moroi they studied it because the Y nu, the corresponding Yukawa coupling is so small. This could be a non-thermal cold dark matter candidate. You could produce it by what now we say quote-unquote freezing mechanism. For example, the other particles in the thermal distribution, they will decay, sprinkling Wright's neutrinos, and gradually their number density will build up. That's the idea. Detection is safe here because the interactions are so weak anyway. And then the other group, the group here, they have studied another case that is in the supersymmetrized version of the scenario. There is a soft SOSI breaking trilinear term that corresponds with, so I'll show you the superpotential here. So this is the superpotential. This is the usual Yukawa, and this is the corresponding trilinear. And this trilinear for M-supra models is just proportional to the Yukawa, so it's usually taken to be small. But the detail, of course, depends on the SOSI breaking center. And this could generally be phenomenological. It could be taken to be large. By large, I don't mean like 100 GeV or something, because my Yukawa for a 100 GeV Majorana mass is about 10 power minus 6 or so. But this could be like 0.1 GeV or something, for example, this trilinear term. But a large trilinear term, however, induces significant left-right mixing in the system. A significant could be like 1 or 2%, but that is good enough in most cases. So So this is the scenario those groups started. And we continued with that. Here is the implication for neutrino mass again. This is the same loop, a neutrino, Gagino, and S neutrino, because as you see that, because I have taken a Majorana mass here, there is a corresponding soft term, and again there is a CP even CP or split, and that will always contribute to the neutrino mass at one loop. So I could not make the trilinear parameter arbitrarily large for arbitrarily large Majorana mass in the soft sector. So this is guided by this. The labeling is wrong. This should be G 10 power minus 10, not E G. So this is the allowed parameter range. As you see that the neutrino mass already constrains the trilinear parameter. You have to take it small if the splitting is large and vice versa. So these are the seminal papers first one. The second one is with the right neutrino and they discuss the loops in great detail. This is the status of the thermal right neutrino dark matter. Almost everywhere sadly ruled out, unless you hit a resonance where you could satisfy the Rayleigh elements. That's what we are doing here at low mass. Of course, this is a Z or Higgs resonance that would give us the right Rayleigh. Here we kept some of the heavier Higgses in the MSSM, and they could give the right Rayleigh. But normally, the very allowed mixing is ruled out by direct detection. That's the point. So as we see that the only option is either to hit a resonance and satisfy the Rayleigh and direct detection both, or have some non-thermal production mechanism for the S neutrino candidate. This is the status of it. Now collider implications, again as I said that our motivation to study different non-canonical MSSM LSPs is how the SUSI searches could be affected by them. One of the motivation is that. So after the dark matter status, I go to what would be the collider search status, and here I pick the Higgsino spectrum. Why? Because okay. So a low Higgsino mass corresponds to the so-called low fine-tuning in supersymmetric models. There are several papers by Bayer, Tata, and collaborators who have explicitly shown this, and this is electroweak fine-tuning, so the stops could be still somewhat heavy. If mu appears, this mu parameter, the Higgsino mass parameter appears in the superpotential, it will contribute to the fine-tuning measure at the tree level directly, and therefore a low mu would correspond to a small fine-tuning. So now when we are so pessimistic about SUSI, I think it is important to quantify the cost that we are paying for the fine-tuning cost that we are paying. So this the limit on mu parameter is something that is very interesting for us and for several other groups. How far LHC is pushing up on mu, and this is why we take the Higgsino spectrum. Here for the simple model is just the Higgsino, and Gaginos are kind of very heavy. So because if we make the cascade complicated, of course there could be branching in several states, and the study would be very messy. So in the simplest case, when we have a low mu parameter, Gaginos are taken to be somewhat heavy, like 500. If mu is like 300, then Gaginos would be like 1 TeV or 2 TeV, something like that. So they are out of the reach of LHC production. Here, however, the thing is that although they are very heavy, they could contribute to the hierarchy of these mass splittings. So here, normally when you have Gaginos decoupled, what you get is neutralino 2, a chargino in between, and a neutralino 1 here. One of the neutralinos are so-called symmetric state, the heavier one could be the asymmetric state, or vice versa, depending on sign of these are the things. But the point is that there would be two neutralinos, one chargino. Typically, what would happen is that the chargino will fall between the two neutralinos, and the mass splitting would be ordered a few GeV. That's it. And however, you could play with the Gagino masses M1 and M2, which are completely outside the reach of LHC, like as I said, 1 TeV, 2 TeV, 3 TeV, and you could change this hierarchy of the states. So this chargino coming between two neutralinos could go to NLSP chargino, and then two neutralinos above that. That is the spectrum. this has significance because this spectrum would be otherwise ruled out in NSSM because it will predict charged LSP. But now that this weakly interacting S neutrino is there, this parameter space is allowed. This is open. And this can be probed. I mean, so this is something interesting that the Gaugino masses, the Gaugino mixing can play a role even in the compressed Higgsino spectrum in kind of adjusting the hierarchy as well as the decay modes. Which decay mode would contribute how much? I will show you the next one. Here we take, so this is the compressed case. This A and S just stands for symmetric and antisymmetric Higgsino state. These are the neutralinos and the Chatterjee is there. As you see, so people have studied the compressed spectrum as well before. And again, my supervisor, Idris is there, and Julis and Pamela, their paper is there. This is compressed Higgsino spectrum. Dedicated study for that. So, but this was within NSSM. We are doing it with S neutrino LSP now, and we assume that we are only looking at prompt leptonic decays because now that the U covers are weak and so on, one could also go to the displaced region. Not many studies there, but we for this work we try to stick to the prompt decay only. So this Chatterjee going to leptons neutrino, this is a prompt decay. We just ensure that, and here are some plots showing. So this 10 power minus 13 is kind of the borderline between the displaced vertices and prompt decay. So that's why we show where we fall above it and where it goes below it. So that's, we are only considering prompt decays for this study. This is the parameter space for scan. As you see that we have kept the mu low, tan beta is also, and P mu, the trilinear parameter, is about 0.5 GeV for the scan. Here are the plots. Why we show this delta n is that by carrying M1, M2 for the fixed mu, you could change delta n, as we said. And why is it important? Because the alternative decay modes for the Chatterjee and neutralino, as I show here, see the alternative modes, neutralino 2 goes to, if it does not go to neutrino, it would go to Chatterjee and charged pion or very soft jets via off-shell W. Or it can also go to neutralino 1 and again via very off-shell Z because the mass splitting is like a few GeV order, and two soft jets. That's why it will go. And same for Chatterjee if there is a neutralino below it. So the point is that these are all three-body or effective two-body decays if you take the hadronic state in itself, depending on the mass splitting. And for three-body decay, we know that decay weight goes as delta n to the power 5. So a small change in delta n would immediately change the branching ratio from the leptonic state to the other non-leptonic states. The branching ratio can be seriously affected even if your M1 and M2, the Gaugino mass parameters are sitting that high. This is simply because the S neutrino, the LSP is somewhat weakly, the coupling between the LSP and the NLSP is weak, and the three-body and two-body decay competes in this region. So this is the parameter scan, and this is the delta n, which can be varied for the same mu, same Higgsino mass parameter, but simply varying M1 and M2, which can be varied widely, as we see, as well as, so correspondingly the branching ratios would vary. Branching ratios are important for LHC because, as we know, production cross-section times branching ratio gives you an estimate of what signal should be looked at. And this can simply be varied by carrying N1 and 2 up there. So we are interested in the bound on the mu parameter, but as we see that without knowing exactly what M1 and M2 is or how much the Gaugino admixture is, it's hard to kind of give a model or parameter independent bound on just mu in this case, just because of the nature of LSP, I emphasize again. So this is again for negative mu. The plots look somewhat different, but the features are the same. Here there are some hints because this flip between symmetric and asymmetric state that can also be achieved by carrying M1 and M2 above 2 TeV, 3 TeV, where your mu is sitting as 300 GeV, but the mixing can be tuned from there. So this can affect the branchings and this can affect the detection prospect. So what are the signals that we are trying to look at here? Monolepton plus less than 1 jet plus missingnity, as well as dilepton, which includes SSTM as well as LL bar plus missingnity. with zero jet. Zero jet is important here because dileptons or SSTLs are routinely looked for gluino searches and so on, but they come with a multitude of jets. Background suppression would be more efficient without with the jet multiplicity reduced. So in this case, you could get it in the simple spectrum by varying M1 and 2 up there and so on. So this is the simulation. Of course, Chi1, Chi1 and Chi2 by 2 pair production does not matter so much. The others do. Here is the signal, as we say. And we see that already same sign dilepton is pretty much constrained for to be less than 4%. Actually, this is a bad time to give talk because right after Morion, all results will be updated. But and these are old. But this old meaning this is 2018 paper. So, as you see that effective period less than 4% for mu 300 order 300 GB. That was already there in that time. This is from SSTL, same sign dilepton, but which had a pretty good bound on the system. So again, we benchmark it, and I would like to emphasize that for the compressed spectrum in general, when your Chatterjee is going to Neutrino and the charged pion and so on, there are other dedicated studies because those are very interesting. It studies the compressed fixed spectrum, but the soft pion. So detecting the soft tracks are very important for that. And there was an IPMU group, Satoshi Shirai and all, they were studying like whether in the inner baseline there will be 2 hits or 3 hits in constructing the pion track and so on, and trying to detect that kind of spectrum. So that was pretty interesting, but that needs a separate dedicated study for this fixed spectrum. We are just looking at the branching fraction to the brown leptons. That's so here are the results for our benchmarks. Benchmarks are optimized to you don't need to optimize much because the signals are there anyway. They come very nicely, monolepton or dilepton or SSTL. The first table was showing some checks against existing cards. The references I did not write down the numbers, but it's there in our paper. So the existing cards, and we see that these benchmarks could be pretty insensitive because many of them require very high integrated luminosity to probe them. However, we optimize the cards, of course, the usual signal to background analysis, and this can be brought down to sigma and 5 sigma significance. Can be brought down. The first table is for monolepton for all our benchmarks, a few hundred, and I would again like to stress that this is all for a low mu. 3 of the benchmarks have mu around 300, and 2 have 500 and 400. So it's like all below or around 500. We are not pushing on mu. So again, these are the tentative 3 sigma and 5 sigma integrated luminosities from our optimized cards for our benchmarks. The second one is for same opposite sign dilepton. Here again we have kept both flavors of the neutrino. This is another interesting thing, that the flavors of the neutrino, we kept E mu both light. Normally, if I remove one of them, the background would reduce a bit, because here we are studying by lepton, I mean E and mu both. So the signal significance would increase a bit if I remove one of the steps. Also, if I could bring down tau, there are other people who are studying with tau's neutrino, and then the signal comes, the lepton becomes tau, and you have to tag it in the hadronic mode where the efficiencies are low. So pretty much lower mu could be allowed in those cases, and with one flavor probably a little higher mu could be allowed. But generally this is the scenario, that mu around 300 to 500 is doing pretty well in this case. Finding it is not difficult. Okay. So these were my SUSI part. So my LSP within dark matter within well-motivated model, and the consequence and its consequence in terms of collider signatures and the dark matter status, so detection and this thing, radical matters. So now we come to a not so well-motivated model, many of you might say, but this is a model just for dark matter, but this time dark matter is self-interacting. Now the self-interaction, of course, this This is unfortunately a blend of astrophysics and particle physics, and we always doubt are there any astrophysicists here? Because I don't know much about astrophysics, but people always apparently doubt that, okay, the 2 could be a 20 in astrophysics, so it's not so clear. So the evidences that I present here may not be as precise as the particle physics part. But, okay.
If I might say, this evidence is much more concrete than anything you can say for Susie. This is much more motivated than Susie.
Okay.
Because
Okay.
all these things are observed.
Okay.
So, I beg to differ.
I should say there is a simulation that you match with observation, and simulation is from a lambda
Okay.
CDM assuming no baryonic feedback and so on. So there are catches, but yeah, of course I make slides so that it looks more motivated than. But anyway, here core versus task is a long-standing issue, and this is, I think, this really stands. I think it simply says that the lambda CDM, the usual dark matter model, the VDM, non-self interaction, it predicts in simulation generically without baryonic feedback. Of course, task peak profile, which is a profile that is much it goes as 1 over r square or so as r approaches to the center. But observations have been showing that the profile, dark matter profile in the center of the galaxy or smaller objects might be more like core-like. So I think this is a thing that is standing. Missing satellite, this 99 paper, there is almost a consensus. I think that this is not a problem anymore, because people have seen with the more modern recent observations, many of the dwarf galaxies are actually very faint. They were not observed at that point. These are Milky Way satellites. Lambda CDM predicts more, and we observe less. So one reason could be that they are dark matter dominated, and they simply don't have enough luminous baryons for us to observe. And recent days, there are more and more such satellites have been observed. So I think this is not a serious problem anymore. Too big to fail still, I think, remains. This is a recent, rather recent, pointed out by this group. First, this simply says that prediction indicates massive satellites, whereas they study the circular velocity and find that I think the predictions say that the circular velocity of objects in the satellite, which is a measure of the mass of the satellite galaxy, would be more than 25 kilometers per second, when all observations fall well below 25. So that means that the host galaxy is not heavy enough. Then the question is why the heavy enough host halos or subhalos are not showing up, and maybe they don't have stars in them, visible stars in them, and are very faint. But then they are too heavy not to support a star formation in them. So that's the argument. That's too big to fail. So I think that stands. Diversity problem is another more recent thing that I am reading about. And of course, one of the solutions to these problems is like, so if I take too big to fail and core versus cusp as more serious, let us say, and they mostly say that some of the massive subhalos predicted by lambda CDM simulations are absent. Some code-like, cusp-like profiles become code-like profiles, which means they are more flattened, so less massive. Baryonic feedback could be one reason. This involves supernova bursts, like if there is a supernova form and it bursts and takes matter away from the subhalo. That has been studied as one reason. Tidal and reconnaissance stripping, and but these effects apparently are also present in so-called field galaxies, which are away from other bigger astronomical objects. So the stripping thing does not really work for them. So it's not clear how to solve all these issues with baryonic feedback, for example. And the other proposition is to have a self-interacting dark matter. The advantage is that if the dark matter self-interaction is strong, the moment the simulations try to say that they peak at around the center, and then the dark matter scattering rate also increases, so evenly distributing the velocities around. So again, disperses particles from the center of the galaxy to outwards. So that's what self-interaction is supposed to help. There is a hint by pointed out by this group, but this again was contested by another group, and we don't understand much of astrophysics, so we are just shuffling between arguments. But there is this observation of Abel 3827 using strong lensing, and they were seeing other galaxies falling in that, and they were trying to, using strong lensing, they were trying to estimate the mass, and offset between the dark matter and the baryonic mass would give an interaction and a constraint or an estimate of interaction between dark matter particles. That's the idea. And they said that signature, if I may say this, I don't know, sigma is really low, and this is the astrophysical sigma, but about 1.5, I think, barn per GeV was the estimated signature. And it was slightly different for if the interaction is a long range or a contact interaction. So that was their observation. Then other astrophysics groups also contested this. They said it's consistent. So I don't know what is that. Because the stake is high here, because if dark matter has self-interaction, a lot of dark matter models, particle dark matter models, are just ruled out immediately. So the stake is pretty high. So we are, as particle physics guys, we are just keeping an eye on what is happening there. Here are the so observations also prefer some velocity. How much time I have?
Yeah, what?
10 minutes. So these are the recent, this is taken from a recent review, and these are the constraints and hints, you might say, on various scales and various velocities, because various astronomical objects support various velocities. Larger objects support more velocity of dark matter particles in them. So this is the status. And now, so what do we need to have a self-interaction, large self-interaction? Simplest way is lambda 5 with lambda large. That's fine. The only problem is lambda pretty much, since we are particle physics guys and we run RGs often, you take large lambda, it also requires a low mass, like MEV mass, for example. If I want to have this 1 barn per GeV kind of self-interaction. So if I take a large lambda of 0.7 at MEV scale and I try to run it, it becomes non-perturbative pretty soon. And there are, of course, strongly interacting models and so on. We have constructed various models, but my personal liking is, from perturbative perspective, is that a model with a light force carrier. That helps because that gives rise to so-called Sommerfeld enhancement in the system, because dark matter particles are coming at low velocities and the extra force carrier simply acts as extra attraction between them. So it's like particles coming and getting attracted. Effective cross-section of dark matter going to dark matter becomes pretty large in the presence of a light mediator. That's the idea. So what we need, we simply again, we take an extra U1 gauge group, local gauge group, because global symmetries have routine problems with gravity effects at high scale, and recently Nombrini and collaborators have shown that even if your dark matter, the symmetry that protects dark matter is broken at Planck scale, even that could rule out the effective operators that you can write from that could rule out the dark matter model. So we take a local symmetry. So in a way, this model is still minimal because we take a U1 local motivated by that, and of course we need two Weyl fermions. This is just for anomaly cancellation, and a gauge boson comes for free. Now, because there is a gauge boson, this would be otherwise massless. We have to have either Stuckelberg or Higgs mechanism to give it a mass, because otherwise it would be cosmologically inconsistent, where BBN, the success of BBN would rule it out already, and structure formation as well. If there is too much relativistic particle dark radiation, so to say, then the model will be ruled out anyway. So we have to give it a mass, and we prefer Higgs mechanism. So this dark Higgs comes in. So that's the minimal ingredient for a continuous local symmetric model of dark matter. Consequences here, I will skip slide, but this is like, the point is, in the spectrum you have these extra particles, one extra light Higgs that we want to keep light, because as I said, Sommerfeld enhancement is important for us. Dark gauge boson would be there. And of course, the dark matter, since there are two Weyl fermions, they would eventually form two, in the mass eigenbasis, two fermionic states. And this is, one of them would be stable, the lighter one, the heavier one would eventually decay. So that's a simple model. And how to talk to standard model? Of course, there is one Higgs mixing H1 to H2. H2, when I say H2, it's the standard model 125 GeV. And this is the dark age boson. So this has kinetic mixing with the U1B boson. It effectively mixes with the Z boson after rotation. So that's the simple model, kinetic mixing, and it will be 2 portals. We assume kinetic mixing to be small for reasons that I described. And the Higgs mixing, we will try to put a bound on that because we want to know. This is also motivated by the philosophy that if we don't see anything at LHC, either the BSM theory is very heavy and can be studied by effective operators or by loop effects, or maybe it's very light but weakly coupled. So we want to see how weakly coupled this thing is. We prefer the second one, so light but weakly coupled. We want to see how weakly coupled it is. So 2 portals are there, the Higgs portal and the kinetic portal. We want to see how much constant we can get from the portal. So this is the Sommerfeld enhancement technology in the Born region, in the classical region, and in the resonance region. You get different expressions. But yeah, much of this is taken for strongly correlated systems people who were actually trying to study electrons roaming around in a screen potential inside matter. So this is not really particle physics here. I mean, not high events. So here is the Sommerfeld enhancement estimate. As you can see that this part is ruled out by bullet cluster down here, and this is how the plots typically look at. These are the resonance regions and so on. This is the mediator, this is the dark matter mass, and the mediator mass is on the y-axis. So the mediator has to be light. This is for a fixed coupling between the dark matter and the mediator. Coupling has to be somewhat large because small couplings, of course, will be in the enhancement effect. And this is a velocity dependent effect, so we always mention the velocity. Small velocity corresponds to smaller dark matter subunits. So we could see that alpha d about 10 power minus 3 or 10 power minus 2 in this region. We could get a lot of points. Remember that H1, in H1 the mediator is light, but we don't want it to be lighter than 10 MeV or so, because it will also ruin BBM. It will have significant effect on the expansion history of the universe behaving as a radiation during or around BBM or decaying around BBM. So points above this is what we would like to consider, and this is the alpha. This is the kind of alpha that is there. We put constraints one by one. These are left constraints from Upal and Delphi on the Higgs mixing sin theta, and you see constraints are weak, and you will go very fast. This is a HC, again signal strength, just from HVV vertices signal strength. Constraints are, the gray points are only the ones that are ruled out. Constraints are again like 0.1 or so on sin theta. And this is a correlation between ZP and this is because of model. This is again H2 to H1 became to 2 mu1s. So constraints are weak up to here because mu1 branching of H1 is weak, and from here light H1's constraints are strong. This is from Atlas, 4 electron analysis. This is the same for Z, H2 to Z. You see that the sigma Sm is about here 10 power minus 4 for Z mass of about 1 to 2 GeV, and these are the jet psi and epsilon resonances that are scaled out, and the analysis works only for 15. So the constraints can be reinterpreted in terms of the portal sin theta, Higgs mixing angle, because we have assumed kinetic mixing to be like 10 power minus 5 or so. So this is the sin theta that we could expect to have from mixing angle excluded up to 10 power minus 4 or so. So this is the talking between standard model and the dark sector. Again, as we push, because we have a light mediator, we push for the flavor and beam dump and stuff like that, and they could also give us up to about this sin square. So again about 10 power minus 4 or so, the charm is slightly stronger. So direct detection is important here again, because light mediator, we keep using effective operator, that approach is no longer works. So here we actually needed the beam-wise kind of distribution, like recoil momentum and how many events at that recoil momentum, that kind of data. And fortunately, DD-Cal collaboration by Felix Kalafer and others, they have released this code that comes with raw data as well. And we could modify that to fit our cross-section, because normally this part is effective. This f of p has lambda q is it's the coupling between dark matter, effective coupling between dark matter and quark. So it's, when this is a Higgs mediation, this goes as 1 over m Higgs square. That's it. That's what people typically assume, and that's how the codes like micrometers and all calculate. But what we need is this momentum dependence, because our mediator is like 10 MeV, and the momentum transfer is also ordered 10 MeV or so for xenon, for example, and so on. So we need this Q square dependency. So we explicitly put it in and compute the likelihood using this DD-calc machinery. And now this is how the bounds look like. Here you can see the f sin theta. Again, sin theta is important. F you can infer from the alpha d. Alpha d 10 power minus 3 gives us large self-interaction. Corresponding f is order 0.1, because alpha d is just f square over 4 pi. So this number is 0.1, and anything else goes to sin theta, the Porter coupling between standard model and this. So from here you can see that if dark matter mass is like very light, we know that light mass recoil is low, direct detection sensitivity drops, and the bounds are weak. We see the same thing here. So if f is 0.1 for a 5 GeV dark matter, sin theta becomes 10 power minus 6. That's already pretty weak for the talking between the standard model and the dark sector from this plot. And for heavier dark matter, the direct detection sensitivity is more because the recoil of nuclei is more, and we get stronger limits already pushing us away. So this is the usual calculation with effective operator. This is the momentum factor taken in. Recently there was a paper from, not recent, but in 2018, there was a paper from Panda collaboration who did a similar analysis. We calibrated, since we modified the code and so on, so we calibrated our results with them and it matches. So this estimation is pretty okay. Now coming to the question whether the dark matter will be thermal or not, because the portal starts becoming weaker and weaker as we see that when we assume that self-interaction is there, and this simple framework which has a Higgs portal as well as some small kinetic mixing. Kinetic mixing we are already assuming smaller than and constraining the Higgs portal coupling. So we see that for thermalization, this analysis is a bit not so accurate because we don't take finite temperature masses and so on, but this could give a pretty clear idea that this is like H1 to H2, the scattering both ways in the early universe at high temperature. So both all particles are assumed to be relativistic, well above electroweak phase transition. Like we go up to 10 power 5, 6, I think GeV. So all particles, and we compare it the rate of H1 to H2 and vice versa, both ways with the Hubble expansion rate. And we see that lambda mix, the parameter in the linking the Higgs with the dark Higgs needs to be like 10 power minus 5 or so in order to achieve thermalization well before electroweak phase transition. Around electroweak phase transition, thermal effects, thermal wave and so on, they will become important, finite temperature wave and so on. So this analysis does not factor that in. But the order of magnitude estimate, I think, will be fine. So we need this mixing thing about 10 power minus 5 or so, the parameter there. What does it mean? That means after an extensive scan, we hardly get any point that has a thermal relic abundance at high masses especially. We struggle to get a thermal relic, right thermal relic with not because, so if you just blindly calculate with micromegas and so on, it does not check the thermalization before. It simply computes the relic abundance. It might give you some relic abundance, but that's wrong because two sectors don't thermalize in the first place. So the cross sections that it computes would be wrong as well. So here we struggle to get a thermal point. Here is our benchmark after a lot of struggle by postdoc. So he gave this. This is like 2 GeV of dark matter mass, and the dominant channel is H1 annihilation channel, and the self-interaction cross section is 0.11 per GeV that we need. But this is like 2 GeV. Clearly, you see the CT, not CT, but the thing is that to evade direct detection, we had to push it to a very low mass. Simply put that. So here are some future limits. So direct detection already constrains it, as I said, but here are future limits from Atlas and other experiments like SHIP and LZ and so on. LZ is slightly in the heavier one, but SHIP is pretty much in our. Also, there were some cosmological constants that I have not shown from both BBN and astrophysical from supernova, cosmological from CMBR that I have not shown. So the story is that again it's the important thing to note is that to constrain H2 to ZT, the important final state so far seems to be 4B1 final states. ZT going to 4B1s, they have the best prospect according to the present cards available. Note that these light ZTs are heavily boosted, so the mu1 separation is very low. So recent CMS analysis, they are considering like a di-mu1 object which clubs two mu1s. One has to do something like that because the typical mu1 isolation cuts that we put data are 0.2 or so would not give any signature. So that is not probable, but Atlas and CMS, they are trying to come up with lower mass searches sensitivities for this ZT. As you see that this Atlas thing already goes up to 2 GeV of the ZT mass. So it's pretty boosted ZT and pretty boosted mu1. So the point is 4 mu1s are the best bet so far. The numbers that we could get, and here we see that again the implications on sin theta is again like 10 power minus 5 or so from here that you see. So because H2 to ZT is directly proportional to sin theta. So the branching is proportional to sin theta, we consider the portal again. This is 10 power minus 5. So competing with low mass DD in the self interaction region, but for higher mass dark matter, still direct detection takes care of it, the portal. If I assume large self interaction. This is, as I said, that we have assumed only the kinetic mixing portal to be large enough so that decays are prompt mu1s, but displaced searches are becoming increasingly popular these days. Triggers were not set in the first few runs, but now I hope in future runs more and more displaced vertices and late decaying objects would be searched for. And this is just an illustration where the ZD would decay. This is a 14 TeV, 3000 to 1 inverse. This is a 27 TeV. So you see color gradient moves up because ZDs are more and more boosted, and the decay takes place depending on where the decay is. This part I think I'll really skip. Okay. So I go to, this is just a preheating. So since we said that thermal benchmarks are hard to get, and we show one of the non-thermal production mechanism right after inflation where the scalars can be produced. This is preheating, and this is a well-known mechanism. Actually, we apply it for dark matter and try to see that the scalar mediators can be produced, and then if you have prefer fermionic dark matters, you could do a dark freeze out or something to produce the dark matter model. Conclusion, acknowledgement. Sorry about that. 8 minutes delay.
All right, thank you, Arindam. Are there any questions?
So for your model for the self-interaction, really all you need is a Sommerfeld going on like that, because the Higgs connection is not needed.
Well, that is always there. In particle physics, we believe if you set a parameter to be small, it's not dictated by your symmetry, then that is a
But
unique.
I can set it up, but that's nothing to do with the large cross-section again.
As I said, we had two motivations. Yes, it has nothing to do with large cross-section, that I had. But we have two motivations. That this dark sector, how strongly it is, it's a weakly coupled sector we know, but how weakly it couples in the light of the current data. That's also the one thing that we wanted to account for in the study. The other thing is dark matter parts of the self-interaction.
So, but that weak coupling can come through other sources. Like
you have to,
it does not have to go through Higgs, because Higgs is a large constraint on the whole thing. One can bypass the Higgs.
I mean, if
suppose one builds a model where dark matter is connected to standard model particles, or something else, that gauge interactions and all this stuff. And I don't have the Higgs. Just Higgs portal is a bad thing.
I mean, if you have a scalar phi dagger phi h dagger h is there,
but
if you don't have any scalar in the model, you have a vector mediator or something.
That's up to the coupling. You put a lambda 1
yes,
or that.
because we are trying to constrain the coupling. So we have it there, and then we try to see how various data can push it
But
down.
suppose right from the beginning,
You could set it to 0 and not study the constraint. That's an option. Yes.
but that does not do anything.
To the self-interaction. No. It does not do anything. The self-interaction gets connected to this portal constraint via the direct detection. Because at one vertex you put the f, other vertex you put the sin theta.
All right, well, Arindam will be around for the entire week. He'll be in for this office. Let's thank him very much.